Okay, Unit 8, Notes 2. It's all about talking about light as a ray. So we're specifically going to talk about how light mixes into separate colors and then how light acts like a ray when it behaves with mirrors and reflections. So we're going to talk about how mirrors work and how different shapes of mirrors can produce different kind of representations in our eyes. So let's first talk about light as a ray. So what is a light ray? Well, it's an imaginary line that we can draw running from the direction that light travels. All right, so if we had, let's say for instance, we have the sun and then we have the earth, and in between there, we're going to draw a straight line because that's the way the light rays are traveling. So those light rays are just an imaginary line. And the study of light, when it behaves as a ray, is called geometrical optics. So you can kind of play around with light and study it and manipulate it using lenses and mirrors to kind of change its behavior. So geometrical drawings are used to represent the path of that light, and we will get practice with that in the future. So just I'm gonna go ahead and hide here, and then we can continue on with the notes. So let's say we have an image of a tree right here. There's a couple of ways you can look at that tree. Of course, you can look at it straight on, which isn't represented here. But what you can actually see, like in a lake, like a very still lake, you can see an image of that tree that is upside down within the lake itself. Now, what you are actually seeing is the reflection of that tree. And of course, you know that. But the way that reflection works is like, how do those light rays behave? Well, you kind of have to like find the angle at which your eye is viewing and the angle of the tree. So the tree is bouncing off here. The angle of incidence is equal to the angle of reflection here, so that it goes on here and it bounces this way. And then that's this part of the tree. And then the top of the tree does the same thing. It bounces off of the surface here. There's an angle of incidence and then an angle of reflection that goes towards our eye. Now what we do here is that these reflected rays, we're just going to extend them out like an imaginary line. And we're pretending that they're going to intersect here, and that's where our image occurs. If that was a lot, don't worry about that. We're going to cover mirror reflections a lot more thoroughly in the future, so just hold on tight. But just know that a light ray, once again, are imaginary lines that we can draw to study the geometry of how light behaves. And yeah. So there's a couple of different types of reflections that we can talk about. The first one is called a specular reflection. Now I'm going to focus on the word specular. So spec or spect with a T at the end. It's a Latin root that means to see. So this is a type of a reflection that you can actually see. So a specular reflection occurs when light waves bounce off of a smooth surface. So the key thing here is that the light has to bounce off of a very smooth surface. Smooth surface is the key there. So for example, a mirror would be a very smooth surface. Sometimes you can see a reflection in glass when it's if it, like one side is lit up and the other side is dark, you can see a reflection in glass. Sometimes off of like a really shiny car, you can see a reflection. Just basically anything smooth, you'd be able to see a specular reflection. Usually you see a true reflection of the object, like with mirrors or windows. All right. And just to talk about the law of reflection, I've mentioned this before, but we're going to mention it again. If we have the light ray traveling down and it hits a flat mirror just like this, it's going to bounce off at the exact same angle to this perpendicular line. This perpendicular line is an imaginary line that's coming off of this mirror. So this angle here from this incident ray to this perpendicular line is the exact same value as from the perpendicular line to the reflected ray. So that's how reflections work. All right, so that's the angle of incidence, and it equals the angle of reflection. All right, so let's say we have someone that's looking in the mirror. Let's say it's this female that is trying to go to work. She's got her briefcase or whatever, and she's looking in the mirror to see how she looks in. Let's say she's looking at her hair first, and then she wants to look at her shoes to see if her shoes match her outfit or whatever. So first of all, there's her eyeball, and that's her source of where she's looking. She's first looking straight forward, and imagine as if the reflected ray were to go straight this way. It's a dotted line because that's an imaginary line until it gets to the top of her head. So that's the reflection right there. So it goes from her eye to this mirror, and then it goes back here. All right. So even though this is the incident ray, this is where the light is actually coming from. this is what she's viewing. She's viewing as if it's through the mirror. So the reflected ray is what she's seeing as if it's on the opposite side of the mirror, right? And then she can do the same thing with her shoes. So the shoes are sending a light because anything that we can see is basically bouncing light off. So it's bouncing light off of her shoe, hitting the mirror, and then going straight into her eye. But when she looks at her shoe in the mirror, it appears as if it's on the other side. And I can kind of show you like a funny video clip right now that kind of demonstrates how mirrors behave very similarly to like if we don't really think about it, but it's almost as if there's like a separate room beyond the mirror. So I'm going to show you a little clip really right now. Okay, so in this video, this is basically just like a little prank show from some country. I think it's like Germany. And basically what's happening here, I'll try to rewind here so we can see. There's a woman who's right here. She is pretending to be in a mirror. So basically there's a piece of glass right here. And there's a room on the opposite side of this piece of glass. That's the exact mirror image of the bathroom this woman is in. And her twin sister is actually right here, her identical twin, mimicking all the motions that this woman is doing. So here's a little prank where this woman comes in and she's trying to like wash her hands. She's looking at this woman and then she tries to look at her reflection. But obviously since she's looking at a piece of glass, she's completely puzzled as to why she doesn't have reflection. But she's looking at the glass as if it's a mirror, because our understandings of mirrors is that there's like a virtual room on the other side of the mirror, which isn't really the case, right? So it's almost as if there's another room or another person on the opposite side of the mirror. So that's just our kind of understanding of how mirrors work or how reflections work. So a diffuse reflection occurs when light waves bounce off of a rough surface. So we're no longer talking about like a smooth surface. We're talking about a surface that is going to be rough, and it's not going to be bouncing back the reflections in the same direction just like the smooth surface did. So most of the objects that we encounter are going to be diffuse, where they reflect kind of like a rough reflection, so we don't actually see a true reflection. We just see like kind of like a shimmer of light on top of them. And this occurs when most objects we see, and allows us to see shapes and colors of objects. This is what kind of gives us the ability to see textures for a certain object. Like if I were to show you, let's say I had a piece of sandpaper, and I would just to show you that piece of sandpaper across the room, you would be able to identify that that is a rough surface simply just by looking at it and seeing a diffuse reflection. Versus if I came up to you and showed you a piece of glass, you would also be able to identify that it's a smooth surface because of the surface reflection that you saw earlier, or the spectacle. So the next topic that I want to talk about is color. So what exactly is color? Well, in our perception, the property possessed by an object of producing different sensations on the eye as a result of the way the object reflects or emits light. All right, so in a handful, basically what that means is color is a way of our brains interpreting a certain wavelength of light. So we have eyeballs, obviously, and inside of our eyeballs are these things called rods and cones. And the cones are actually responsible for us seeing different colors. And color is only significant to living things with eyes. It does not mean anything in terms of physics. So color doesn't really exist outside of the human mind. So for things that can't see color, color doesn't matter, right? So if you were to ask a blind person if they're blind from birth, how they perceive things, they don't perceive anything in color, obviously. So for the human mind, basically, color doesn't really exist outside of that. Color is interpreted in our brains and technically does not exist outside of that. So just to emphasize that one more time. But that's not to say that it's not useful. So color is definitely useful, but we're going to talk about how we interpret different colors and how we are able to see colors off of a surface. So the color of an object is what determines the color of light that is reflected to our eyes. I want to make that really clear. The color of something that we see is the color of light that is reflected to our eyes from that object. All right, so example, if someone was wearing a blue shirt, the only reason why we can see that someone's wearing a blue shirt is because the shirt is reflecting blue light. It therefore is absorbing every single other color of light. So it's absorbing red and green and yellow and everything like that, but it's only reflecting blue light. And we know that's possible because we know that white light is what is usually illuminates the objects around us, and it is a mixture of all the other colors of light. So white light, I've mentioned this before once or twice, but white light, which is like for instance the sun gives off white light, or most light bulbs can give off a certain shade of white light. It is a mixture of every single color of light that exists. And we talked about additive mixing and things like that. So objects that appear to be white in color, all they are doing is reflecting all the colors of lights to our eyes at the same time. So objects that appear to be black in color are actually absorbing all of the colors of light and reflect nothing to our eyes. So for instance, if you wanted to go out for just go play some sports outside in the middle of the summer, and you have two options. You can either wear a white shirt or a black shirt. People that would wear a white shirt would actually feel a lot cooler because the light is being reflected off of them. So all of that white light is being reflected off of them. The shirt is not absorbing it and then turning into heat. Whereas a black shirt would, yes, absorb all that heat and all of the light. And this is how we can split the white light into separate colors. You might have seen this before, like in another lecture that I've done, or like in a rainbow. So this is how rainbows scatter the light, the white light from the sun, and then separate it into its separate wavelengths. And the reason why this is happening is because once the white light enters this prism, the light starts to slow down, but it's slowing down at different rates because of the different wavelengths. So they will bend at different rates. All right, so just to kind of re-emphasize the point here, a blue object is going to absorb every single color of light except for blue. So that's why we can see that it's blue, because it's reflecting off of it. Same thing with a red object. A red object is absorbing everything except for the color red. All right, and then white objects repel all light, and then black objects absorb all light. I mentioned this before, and you've probably seen it in one of the Notes 1 lectures, how every single color is a mixture of red, green, and blue light. All right, so what I have here, let's go talk about this, and then I'll come back to that. So pigment is a property of a material that changes the color of light that it reflects, right? So all possible colors are made of pigment made from the combinations of three primary colors. There's magenta, cyan, and yellow. These are the primary colors of paint. I'm sure you are aware that you learned in art class that red, blue, and yellow were the primary colors of paint. But it's actually, if you want to make every single color of paint, you would get magenta, cyan, and yellow. If you've ever been to Home Depot or Menards or a Lowe's Home Improvement and asked for a can of paint, and you saw how they were mixing the paint, every single paint can that you buy at one of those stores is going to be white. So every single paint can off the wall is white. You take it to the counter, you then tell them what color you want, and in the computer it will tell a certain cartridge dispenser to dispense 3 different colors. It'll dispense magenta, it'll dispense cyan, and it'll dispense yellow in different quantities. Right, so if you want something that's closer to green, maybe it'll dispense a lot of cyan and yellow and only a little bit of magenta, and then that way it will mix the paint for you, and that basically we can make any single color using these primary colors. But for the primary colors of light, going back to this, continuing on, this is subtractive color mixing. So when all 3 pigments are mixed together equally, the resulting color that is then created is black. So I kind of talked about how printers sometimes use color ink, the cyan, magenta, and yellow to make black. You can still do that with any color paint. If you were to mix all the colors equally, you'd get black paint or black pigment. So the colors of light are all possible colors of light are also made up of the combination of these 3 colors: green, blue, and red. I've already mentioned this before, and this is additive color mixing. So additive color mixing is when all 3 colors of light are added together. So if we were to add red and green, we get yellow. Red and blue gives us magenta, and blue and green gives us cyan. And if we mix all of them together, we get a white light. All right, what's really interesting though is that we're going to watch a video here in a second. The color purple doesn't have a natural wavelength. It doesn't have a wavelength of light. It doesn't have a frequency. It doesn't have a wavelength. It is something that we interpret in our minds that doesn't really exist. So I'm going to show you that video, and I'm going to pull that up right now.
Purple is a weird color. The formal name for purple is magenta. And the weird thing about magenta is that you won't ever see it in a rainbow. And the rainbow is supposed to be the full spectrum of colors. So why doesn't magenta appear in the rainbow? And the answer is to do with color mixing. I've always had a problem with color mixing because I know that you can't mix photons together. So you can't take a blue photon and a green photon and mix them together to get some other photon. That just doesn't happen. And yet you can mix paints together in art. Like, color mixing is definitely something you can do. So what's the answer? Well, actually, you can't mix colors together in physics, but you can do it in biology. It's to do with how your eyes work. For example, if I shine red light and green light into your eyes at the same time, if I cross these over, you will see yellow. So when you mix red and green together, you get yellow. And if you look at the spectrum, yellow is in between red and green. So maybe that's the rule for mixing colors together. You mix two colors together, you get the color in between on the color spectrum. And we can test that again. So I'll look at green and blue together. So if I mix green and blue together, I get cyan. And cyan is in between blue and green on the spectrum. So that's great. You mix two colors together, you get the color in between. But why? Why is that? Well, your eyes can't measure the wavelength of light directly. So it's not like a photon comes in and it's, 200 nanometers or whatever, and it detects that. Instead, you have these cone cells at the back of your eyes that are sensitive to different parts of the spectrum. So when red light comes into your eyes, there's a set of cones that fire and tell your brain you're looking at something red. So we'd call those the red cones. There's another set of cones that are more sensitive to green. So when there's green light going into your eyes, they fire and they send a message to your brain. And there's blue cones as well. So you've got red cones, green cones, and blue cones. So what about yellow? What about when you're looking at yellow light like that? Well, in that situation, you don't have a yellow cone. So what do? Well, yellow is quite close to red, so your red cone fires a bit. And yellow is quite close to green as well, so your green cone fires a bit. So your brain is getting a message from your red cone and your green cone at the same time. And it's deciding, okay, well, I must be looking at something in between those two colors then. And that's brilliant because your brain is perceiving something about the world that it isn't able to measure directly. It isn't directly sensitive to yellow light. It does mean that you can be tricked. And so if I make red light and green light going to your eyes, but no yellow light, you will see yellow anyway. So I've got a red torch and a green torch, and there's no yellow light here. But when I combine them, you will see yellow anyway. And TVs do this all the time. So if you look up close at a TV, you'll see the individual pixels, and there are red pixels, green pixels, and blue pixels. Those are the only colors being produced by your TV. And yet, they can produce all the other colors with this trick of color mixing. So what about purple? What about magenta? Well, what should your brain do if your red cone fires at one end of the spectrum and your blue cone fires at the other end of the spectrum, but your green cone doesn't fire? Does it do the same trick? Does it think, I must be looking at a color in between red and blue? Well, the color in between red and blue is green, and you're definitely not looking at something green because your green cone isn't firing. So in that situation, your brain invents a color. It makes up a color, and that color is magenta. And I can show you that. So with my red and blue torches, so when they combine together, there you see magenta. Absolutely beautiful. And that's why you don't see magenta in the spectrum. You don't see magenta in the rainbow because it doesn't have a wavelength. It's just the absence of green, if you like. Just to show you the full palette of colors that you can see on a TV screen. So you get red and blue mixed together makes magenta. Green and red makes yellow. Green and blue makes cyan. When you mix them all together, you get white. So when your red cone, your green cone, and your blue cone are firing together, you get white light.
All right, Unit 8, Lights and Optics, Notes 2, Practice Problems. We're going to go ahead and work on practice problems 1 through 8. And number 1 says a ray of light hits a plane mirror as shown, so in this figure, and the obtuse angle between the incident ray and the mirror is 150 degrees. If you don't know what the word obtuse means, this word right here, it basically just means that it's greater than 90 degrees. Alright, so that's a greater than symbol, so it's greater than 90 degrees. And of course we can see here that 150 degrees is indeed greater than 90 degrees. 1A says, what is the angle of incidence? So the angle of incidence, I'm going to actually do this in different colors. Let's do like a blue color first. So the angle of incidence is actually going to be the angle between the incident ray, this line, and this line over here, which is called the normal line. The normal line is going to be the line that's perpendicular to this surface. So I'm throwing a lot of terms out at you. But basically, this normal line here, that one, is going to be perpendicular to the flat surface here. And the incident ray is that angle between this and this. And we want to figure out what exactly that is. Well, we have a piece of information here that's given to us, and that it's this angle right here. So that's 150 degrees, right? And another thing that we know is that this normal line is perpendicular. Well, if you know the relationships between perpendicular objects, you know that they always occur at right angles. So I drew a little symbol there. It's kind of like it kind of makes a square here. Right angles are always going to be 90 degrees. So if this whole thing is going to be 150 degrees, this angle, and we're only taking a look at this specific part, this part right here, that's all we care about, we want to subtract 90 from that 150. So we'll do 150 degrees subtracted that 90 degrees that we have right here, and then that tells us this angle right here. So that angle of incidence is going to be 60 degrees. All right. 1B says, what is the angle of reflection? So if you remember from the notes, the angle of incidence is always going to equal the angle of reflection. So whatever angle of reflection that we have here, so I'm just going to highlight this, whatever angle of incidence rather we have here is going to be the same as the angle of reflection. So it's going to stick out. If this was 60 degrees, this is also 60 degrees. So I'm going to go ahead and write that answer right there. 60 degrees. So letter C says complete the ray diagram drawing the reflected ray. So let's go ahead and do that. I'm actually going to use this line tool, make sure it's red. So I'm going to just do a reflected ray coming off of that same origin point, and I'm going to do my best to match that angle here. So that should be it right there. And just to notate, the line from here to here is 60 degrees. And the line, the angle, and then the angle from here to here is also 60 degrees. So just keep that in mind. The big thing to remember here is that the angle of incidence and the angle of reflection are the same. All right, moving on to number 2. We have a couple of fill-ins. Parallel light rays are reflected in the same direction on a flat, smooth surface. So that's talking about like this diagram right here where we have reflections all bouncing off at the same angle. So all of these angles are the same. What type of reflection is this? This is called a specular reflection. So that's just to recall that a specular is going to be where they all go in the same angle. I'm actually going to type that out so just to make it a little bit neater. Red specular. Parallel light rays are reflected towards different directions on rough surfaces. So like over here. On a rough surface, they're going to go in different directions so you don't see an actual reflection. But you see a little bit of a sheen or a little bit of shine to it, so it does reflect some light. This is called a diffuse reflection. All right, so there's number 2. Number 3 through 8, more multiple choice here, so let's go ahead and continue. Light rays reflecting off a rough surface reflect A, diffusely, B, at single angles, C, at all angles, or D, none of the above. We just covered this in practice problem number 2. Light rays reflecting off of a rough surface will reflect diffusely. Number 4, the law of reflection says that angle of incidence is blank to the angle of reflection. Again, we cover this in practice problem number 1. Is it greater than, less than, equal to, or none of the above? The answer, of course, is equal to. The angle is equal to it. Number 5, reflection of light into random directions is called diffuse reflection, the law of reflection, the angle of reflection, or the reflective ray. So if it's going in random directions, again, we covered this in the previous practice problem, number 2, that's going to be a diffuse reflection. Number 6, an apple appears red to your eye because it does what? Does it emit red light, absorb red light, reflect red light, or distorts red light? We can eliminate a couple of choices. We know that apples don't emit light because if we turn off all the lights, the apples aren't glowing. They are absorbing light, but they're not absorbing red light. It's actually because they are reflecting red light that we are able to see the color red. Number 7, in addition to reflecting some light, every object does what? Transmits radio waves, absorbs some light, produces vibrations, or none of the above. So every single object will reflect some light, but also objects can absorb some light. So that's the answer choice there, B. And then finally, number 8, when all 3 additive primary colors are mixed, you see the color black, magenta, cyan, or white. Well, you should know that if we're adding 3 of the colors, we're going to get one of the colors in the center. And it really determines whether it was additive or subtractive color mixing. Magenta and cyan are obviously the incorrect choices because those are either going to be secondary or primary colors. So it's either black or white. And additive primary color mixing, you will add, that's concerning light, not pigment. So when we mix pigment, we get black, but when we get additive primary color mixing, we get the color white. Alright, so that concludes practice problems 1 through 8. We'll see you in notes 2, part 2.